only make progress if all pods are running at the same time. This significantly reduces the load on the control plane, as users can create tens of thousands of jobs waiting in the queue. Actually, queue is not just a workload level scheduler. You can also look at queue from a different perspective. Something like as a quota manager for computational resources such as GPU. In queue, we support quite various configurations for managing quotas between multiple teams, including fair sharing and hierarchical cohorts. At the same time, we support quota management for various types of hardware, like GPUs or TPUs. Additionally, queue allows to give different types of provisioning, like reservations, spot, or on-demand. Finally, with queue, we want to meet users when they are. This means we support a whole portfolio of different workload types, split in 3 major categories. In particular, for training, we support Kubernetes jobs, job set, a set of kubeflow training jobs, and the RAID job and RAID cluster. For inference, we support deployment, stateful set, reader worker set. Finally, we also support more universal workload such as app wrapper and plain pods. In the next slide, let's take a look at the example of the problem users may face on Kubernetes using vanilla kube scheduler without queue. In this example, Adam, Brenda, and Chen create their AI training workloads. Now, Kube Scheduler schedules the pods without any quota checks. In this case, the request exceeds the total amount of physical resources in the cluster, and none of the job can make progress, because every job has some pods which are not scheduled. This is a problem for AI training workloads, because such typically job required to schedule all pods at the same time, as we mentioned in the previous slides. So we end up in deadlock situation. Let's take a look how queue help with the problem. Now, Adam, Brenda, and Chen submit their workloads to queue again. Based on the quota checks, queue admits only 2 of the workloads. All pods get scheduled and the pods are running. Once the workload complete, the waiting workload is now admitted and running too. After a while, all workloads complete, and the researchers are happy. So actually, this is the ideal scenario. However, the quota-based admission has some limitations. First, queue makes admission mistakes, because sometimes it may admit a workload which cannot run due to resource usage fragmentation or node failures. Second, more importantly, queue may preempt a workload, but the newly admitted workload still cannot run due to the fragmentation issue. Finally, queue delegates fine-grained scheduling to the vanilla kube scheduler, which means the pods get scattered across the infrastructure topologies like rack or data center, which is not good for performance of AI ML workloads. Let's imagine the issue by actual scenario. Again, Adam and Chen submit their workload mostly at the same time. Queue admits the workloads but delegates actual fine-grained scheduling to the kube scheduler. So the resource usage is fragmented because kube scheduler does not consider a group of pods with quota. Now a new high-priority workload coming, so queue needs to preempt something to run the workload. Queue preempts the green workload, and the quota check indicates the yellow workload is ready to run. The yellow workload should get scheduled free in queue point of view, but actual part of pod cannot get scheduled by queue scheduler due to fragmentation. So in this case, the preemption did not help, and the yellow workload is likely to hit timeout as it cannot make progress.
Okay, so let me pick it up right here with another piece of motivation for topology-aware scheduling in queue. So in this example, we have a new shiny cluster with new machines, and we are ready to start training some AIs like LLMs. Okay, so we schedule the workloads, but the scheduling of individual pods is still delegated to kube scheduler. So, as in this case, the pods get scheduled all over the cluster. And moreover, in the context of AI training, the pods need to exchange huge amount of data, communication data during the training. And also, one important thing is that for AI training, the communication pattern looks like a ring. So the pods are numbered. The numbers are called ranks, and each rank exchanges most of the data with the neighboring ranks. So this is the pattern for the most popular framework or library, NCCL. And as you can see here, the pods on the belonging to the servers on the left-hand side, they will exchange huge amount of data with the servers on the right-hand side over a high latency network. So this is not good for performance and clearly suboptimal. So this is the picture we would like to have with topology-aware scheduling in queue, where the pods are packed closely and tightly on the servers that are basically neighboring servers on the connected by a low latency network. So let's take a look at how we achieve it with topology-aware scheduling. So first of all, we need to somehow represent the topological information so that queue can benefit from it. But currently in Kubernetes, there is no standard way of representing the topological information. So we want to propose in queue a new convention for representing that based on node labels. So basically, the idea is that every node in the cluster has a set of labels that identify its position in the cluster or in the data center, so that queue can benefit from knowing the relative positions. So let's run over the examples. So the first label indicates the name of the block in the cluster. The second label indicates the name of the rack. And then the last label indicates basically the name of the node. And we believe that with this simple approach, it will be broadly adopted by cloud providers that will annotate the nodes according to the idea. So, but of course, likely, because there is still no standard, the cloud providers will want to use different names for the labels. And more on that, some cloud providers may choose to have different topologies for different machine times, for example, for TPUs and GPUs. So we want to be vendor neutral. And to achieve that, we abstract it out with the topology API. So this new API in queue lets you specify basically the list of the node labels that are that denote the topology. And this new API is referenced from the pre-existing API in queue called resource flavor, which denotes basically the set of machines with common characteristics. So in this example, we have a resource flavor that represents the node pool of 800 machines. And by linking it to the topology, we say that we want Kueue to use topology-aware scheduling on this node pool, respecting the topology. Okay, so now as you can imagine, knowing the topology with the set of the labels and by observing the actual nodes, Kueue is in position to reconstruct the topology tree, so actual topology of the cluster. In this example, we have a small tree with 4 levels that correspond to zone, block, rack, and node. And the nodes of the tree are called topology domains. You may also ask yourself, how do we calculate capacity on the node? So basically, the idea is also very simple. For the nominal capacity, we use the status allocatable field from the node. And from this, we subtract usage coming from the task workloads. These are workloads already admitted by Kueue, so Kueue is aware of them, and pods that are non-Kueue and non-task. We have such pods which are static pods or pods owned by, for example, daemon sets. Now let's take also a look at from a different perspective on topology-aware scheduling in Kueue, from the user perspective. So as it was mentioned before, Kueue supports all various types of jobs. And what is common in them is that they embed the pod template. So we use the pod template to let users specify what type of scheduling requirements they have for the specific pod set. So in this case, we have a job set with 2 pod sets. And with both of them, the user set the requirements. So let's see what labels we support currently. So we have annotations. We have the required annotation. So with this, the user can say that all of the pods in the pod set should be scheduled within the same topology domain at the specified level. Then we have preferred topology. So here the constraint is that it's okay. We prefer them all to be scheduled in one topology domain, but we are okay with spillover to the neighboring domains. And then finally, we support unconstrained topology annotation, with which the users can say that they don't have any expectations about the placement of the pods. And this is actually recommended for workloads which don't require exchanging huge amounts of data, so that Kueue can have freedom to, for example, fill in gaps in the cluster to reduce fragmentation. Okay, so now as we know the user perspective and the admin perspective, let's take a look at the inner workings of Kueue to support topology-aware scheduling. So first of all, as you can imagine, the situation in the cluster can be very dynamic, with nodes popping in and out of existence in some clusters basically all the time. So in order to deal with this situation, Kueue operates in scheduling cycles, and in each scheduling cycle, it starts by creating a snapshot. And the snapshot contains the whole topology tree with computed capacities for every node. Then in the next it considers a workload. So while considering a workload and to find its placement, Kueue executes 2 BFS-like passes through the topology tree. In the first pass, bottom up, it identifies the set of topology domains that will accommodate the workload. In the second top-down traversal, it maps down the identified topology domains onto concrete nodes. Next, it stores the assignment in the workload object and is ready to admit the workload. Once the workload is admitted, the pods are created, but still with scheduling gates, so that in the next step, when we ungate the pods, we can assign them specific node selectors. And it is in this stage that we are very careful about that, so that we make the assignments according to the indexes that I mentioned before for AI training workloads. Again, we call this rank-based ordering. So as you can see in this picture, for optimal performance, the pods with neighboring ranks, they are put within the same node. Okay, and talking about performance, we also run benchmarks by executing regularly training of GPT-2 model from scratch on our state-of-the-art GPU machines. And this at the scale of 32 nodes. And the internal tests demonstrate that with TAS, the training time can be reduced by around 15%. Okay, so let me summarize. Basically, one of the main goals of topology-aware scheduling in Kueue is to improve user experience by reducing the mistakes of admission and preemption. So, because now Kueue becomes aware of the physical capacity of the cluster. Second of all, we want to accelerate AI training and inference by compact placement of the pods and rank-based ordering of the pods. Still, at the same time, we still want to support the same set of jobs that the standard job Kueue supports. And finally, as of 0.11 Kueue, that was released just like 2 weeks ago, we now finally support all of the quota management features that the standard Kueue supports, such as fair sharing or hierarchical cohorts. Additionally, in 0.11, we introduced the auto mode, which allows to reduce friction of adoption of tasks because we no longer require setting the annotations for every pod set in the jobs. And of course, we are not done yet, so we are considering new improvements to topology-aware scheduling. Some of the ideas floating around are to play with different algorithms. So we want to basically balance maybe some users want to balance utilization and fragmentation. So we want to give them the choice of algorithms and make them configurable. We want to also solve the problems of co-scheduling pod sets within a workload. Currently, they are scheduled independently. And then we also are considering tighter integration with Kube Scheduler for better accuracy of scheduling. If you want to be part of the discussions about the future of topology-aware scheduling in Kueue or Kueue as such, or even if you are more interested about what the working group batch is working on and discussing, then I highly recommend you to join our bi-weekly meetings. We also have a Slack channel where you can ask your questions, and we also this year have Project Pavilion 15A, where you can also come and ask questions to the people who are deeply involved in the Kueue project. And also there is a batch working group updates presentation by Marcin. I encourage you to also come there. With that, I also encourage you to try Kueue yourself. You will find more details on our website, and we are ready for some questions. Thank you.
There's a microphone. Yeah, mic over there. You can just ask your questions from there.
Hi, this is Abhishek from IBM Research. So one of the use cases here of TAS was performance improvement. So I wonder if you are planning to include inter-node topology.
Sorry, can you repeat?
Are there any plans to include inter-node topology while scheduling workloads?
Internal within a node, right?
Yeah.
This is currently out of scope. I think this could be somehow married with the plugins, but it's not one of the goals at the moment. But if you have some ideas or such requirement, then feel free to open an issue or come to the meetings so that we can discuss it deeper.
Just one question. Let's imagine that we will deploy a Kueue in the cloud. We can have only 3 information about region, availability zone, and host name. So we cannot have a block or rack. If I understood correctly, you are using these 2 levels in the topology.
Oh, actually, this depends on the cluster provider, cloud provider. So we believe that some cloud providers will expose actually the information about the blocks and racks and more details. And I actually represent Google, and I know that such work is going on. So we, in some node pools, you can already have the labels. Is it your question, or?
Yes.
Okay. So it's like a simple idea. So we hope for broad adoption, and so that this more cloud providers expose this information. Right.
Hi, thanks for the talk. I had a question on the interoperability with the Kube API scheduler. Can it sort of offload scheduling for certain workloads only to Kube, or does Kube have to be the main scheduler in the cluster?
Oh, so you are asking about the future, this tighter integration, right?
Yes.
All right. So basically, currently in Kueue, Topology-Aware scheduling, we only support, we don't support, for example, pod affinities or anti-affinities, or we don't check ports. So we only do scheduling based on what is in the topology. But there are other scheduling directives that are respected by Kube scheduler and not respected by Kueue. So we anticipate we will have users asking to have pod affinities supported. So the question is, how do we implement the support? One approach is that we do this inside Kueue, but this means that for everything we need extra code in Kueue. The alternative is to vendor code of Kube scheduler inside Kueue and delegate the checks to actually the code in Kube scheduler. So this is the idea, like tighter integration. So the idea is that we would vendor the code and ask some specific functions that would do the checks for us.
So that means at the moment it's a requirement to have Kube be the main scheduler of the entire cluster.
That's right. Yes, for the Topology-Aware scheduling, yes.
And the second question, if I'm allowed, could you elaborate a little bit on how a rank of a particular workload is picked?
Oh, rank for the workload, we rely on labels that are set by the jobs, and we have custom code for every supported job to extract the ranks from the labels. So for example, for Kubernetes job, the information about the rank is in the I don't know, completion index label or something like this.
Okay, thank you.
And then we rely on the fact that the user who calls the, for example, PyTorch would assign ranks according to the indexes in the labels.
All right, thank you.
Sure.
Any more questions?
Hello. Yeah. I was just wondering, considering the topological-aware scheduling is mostly based on top of rack switch and then distribution switch distance, is there any plans to integrate stuff like Cisco's CDP for automatic discovery and automatic labeling of those, adding those labels for when you're dynamically provisioning nodes?
This is not part of the queue. We would like to consider this like separate thing and delegate the responsibility of assigning the labels, either to cloud provider or cluster administrator or by some another way of figuring out the distance. But we want to keep it out of queue.
All right, I think that was it. Thank you so much, Michał and Yuki. That was great.